All right, good evening. I'll be presenting the hydropower for civil engineers. The module is HYP 4801. This is the assessment project. And then the focus is on the Maguga Dam Hydropower, the storage versus the runoff river system in the Comparative River Basin. And my name is Jonathan Thabo. My student number is 56964781. And the executive summary of the assessment, the overview, the context, and the main findings. On the overview, as I said, it's the evaluate the performance of the dam compared to the run of the river. The context, the Maguga Dam, its main purpose, that is the irrigation, the domestic use, ecological, supplies for functions, and also the hydropower. And then on the main findings is that the dam delivers approximately 3.34 megawatts of firm power, and the river alternative is 0.84 megawatts. And then on the storage, the storage system provides superior reliability in term during dry seasons. In the background, the dam is between the two countries, South Africa, and then the dam was completed in 2001 with its especially that it was the water supply for domestic use, and also the flows. And then the dam plays a vital role in between the two countries, especially on the water sharing agreements. And also the regional development strategies emphasize the indication of water and energy planning. And then next one is on the visibility of the runoff river alternative is to explore due to its low environmental footprint, the potential cost and advantages. And in this study, investigate whether the runoff river system could match the performance of the dam within the constraints of the Komati basin hydrology. The hydrological analysis. The hydrological analysis, the Komati River exhibits strong seasonality with over 70% of its annual flow occurring between December and March. And then during the dry seasons, the base flow declined below 5.04 at 95%. And the historical drought occurred between 2007 and 2016 resulted in a very low challenge on the operation of the hydropower. The climate projection indicates that a 10 to 20% reduction in the mean annual runoff by 2050. And then these patterns highlight the importance of upstream storage to regulate the flow and provide water security across competing use. And then the last one is the seasonal flow and reliability pose a multi-challenge constraint to run off river energy generation in the region. And then the Maguga Hydropower Scheme, the dam characteristics, the dam was constructed or commissioned in 2001, is an earth-filled dam, and then it has a storage capacity of 332 million cubic meters, and then the surface area is about 10.2 kilometers squares at full supply level. And then the water allocation, as I said, the allocations is for irrigation, domestic use, the ecological release, and also hydropower. On the irrigation, about 260 million cubic meters per year, domestic 15 million cubic meters per year, and the ecological release is 100 million cubic meters per year, and hydropower is supported by or via the On the hydropower infrastructure, it is equipped with a multi-level intake structure to manage the temperature and the water quality. And then the gross head is approximately 110 meters high. And then the use of medium head Francis turbine with high conversion efficiency. Then on the energy output, it's generating of energy is estimated at 7. The generation of energy is estimated at 3.34 watts FEM and 29.3 gigawatts per year of energy. And the storage enables the drought resilience and consistent generation of during dry seasons. Then if you look at the site allocation, the site is allocated 2 kilometers downstream of Maguga Dam. And these are the longitudinal and latitudinal or the coordinates. And then no large reservoir relies on immediate river flow without substantial storage. And the layout includes the intake where the penstock, the powerhouse, and also the canal. On the technical characteristics is that the estimated crosshead of 20 meters is based on the elevation. And then the turbine options is limited to low head designs such as the Kaplan or the, and then again it requires a long conveyance structure, increases the hydraulic losses. And then the hydrological constraints is that is a firm discharge estimated at 5.04 cubic meters per second at 95% exceedance. And then still on the hydrological constraints that an adequate flow during the dry seasons reduces the power to 0.84. And lastly, the high sensitivity to seasonal and daily flow fluctuations. Then on the energy output limitations, the annual generation is estimated at 7.4 gigawatts per hour, gigawatts per year. And then the low capacity factor compared to storage base. Frequent outage expected during low period. Of the hydropower plant layout, where we have the intake, the penstock, the canal, the and the mechanical assessment. But gate with the spillway, crest valve for flood control, and then it was a multi-level intake tower for water quality management, and stilting basing to dissipate energy and prevent downstream erosion. On the electromechanical components, and there is a turbine, Francis turbine for medium head, operating between 40 and 600, and then the efficiency is just over 90%, which is under design conditions. And then the short penstock, which reduces friction losses and improve performance. On the modernization needs, the edge turbine and control system requires upgrade. Then the efficiency losses due to cavitation, sediment, abrasion, and wear. And then on the recommendations is that very variable speed turbine to handle variable head conditions. And then the flow duration curve analysis. This is on the hydrological pattern, the key FDC's observation, and the implications for the designs. A highly seasonal flow regime typical of semi-arid basins, which is over 40% of annual flow concentrated in 4 wet seasons. And then the key FDCs, steep upper curve, high flood peaks are short-lived, flattened lower curve, low base dominate dry seasons. And then on the implications for designs, that Maguga storage buffers low flow, consistent turbine operations. And then in ROR, or the plant would face frequent shutdowns in dry months seasons. The hydraulic and head loss calculations, the ROI system, the terrain profile, which is extracted from the Google Earth, the Pro, and then the estimated cross head is about 20. Obviously, the flow conveys through the long canals and the pipes, increases head loss. Then there's also the formula, the Darcy-Weinbach formula of the head loss, the friction loss, where there's the diameter, the length, and the velocity, the gravity or G, and also the friction loss. And then on the net head estimation, the net head is equal to gross head minus the friction loss and the minor losses. For ROI, and then the net head reduced to 17 to 18 meters under typical flow. And then the Maguga advantage is that the short penstock and high cross head of Maguga keeps head below 3%, and which is it enables the consistent turbine performance and the minimum hydraulic inefficiency. Traffic GIS, the telemetry, drawdowns, and head operation. Then on GIS, the GIS is used, extracted elevation cost, also the supply level, which is equal to what, 625. And then on the reservoir geometry, elevation, you minus the area, you minus the volume curve, the reservoir surface equals to 10.2 kilometers per square, capacity of 302 cubes. And the head calculations, downstream, which is about 75. And then the cross head to power, it's about 110. Supports stable turbine operation in the even in seasonal water level variations. And then the original benefits, large storage volume allows buffering capabilities and ensure consistent water release, power the areas, getting power from there, the irrigation, and also for use. And then this is the typical, there is the actual surface, some of the calculations on the curves that are to choose, and then calculation for the mass balance and reservoir on storage dynamics, the reservoir, the water balance equation, that is the equation, and then the water allocation, the water is allocated in the 4 main areas. And then for operational scenarios, that are used to simulate the water level. Output and turbine sizing on the hydropower equation, this is the equation for hydropower, where there's an efficiency, the density of the water, the flow rate, the Maguga system, 10 of flow enabled firm power of 3.3 megawatts. And then the runoff output, the net head is limited to 18 due to the friction. The firm discharges 104 yield cubic meters per second. That is 0.84 megawatts firm power. The annual generation of 7 gigawatts with a lower capacity factor. And the efficiency considerations that a stable flow support turbine efficiency of just over 90%. The ROI turbine efficiency reduces by variability and head losses. The summary, it's about 3.3 megawatts, 9.7 gigawatts per year. The ROI of 0.84 megawatts power. Losses, under 3% head losses due to short and high head. And then the ROI is just over 10% head loss from the long canals and the low head. And then on the draft resilience is that the storage system buffers seasonal and multi droughts, and then maintains operation during low flow. And then the multiple values is that supports irrigation, water supply for domestic use, ecological flow, and power. Why is limited to electrification with a little operation flexibility. And the storage-based system integrated based in white water. Yeah. Okay. Integrate the seasonal focus and real-time monitoring, and apply dynamic rule curve for draft. And then hybrid energy integration, and install the solar PV panels to reduce evaporation losses, 8 to 10%. Explore ROI plus solar cluster to capture excessive wet season flows. And lastly, the environmental protocols, design adaptive ecological release plan, implement it at least by 2 years with stakeholders that are affected, and ensure 95% viability during drought seasons. In conclusion, that Maguga Dam delivers a significant higher firm power of 3.34 megawatts than the proposed runoff river scheme. And then it generates over 4 times more annual energy compared to ROI options. And it maintains a stable performance during drought seasons, and it supports different water uses. And then the runoff river system is highly sensitive to low flow. And then the strategic improvement should include infrastructure upgrades and reservoir modeling. The hybrid integration with solar PV can enhance drought resilience and reduce evaporation losses. And these are some of the references that were used to come up with the research. Thank you.